the pressurized water reactor concept. We covered the boiling water reactor concept, and we also covered the heavy water reactor concept. Comes next, the high temperature gas cooled reactor. So the question is why to go to a high temperature gas cooled reactor? There are many reasons for this. First, the obvious reason is that it provides us with a higher temperature. This means that it's a higher thermal efficiency. We are taking advantage of the fuel that we have in a more efficient way. We'll see also when we cover the chapter that it also provides us with a possibility of breeding by using the thermal cycle with the thorium. And that thorium is much more abundant in the Earth's crust than uranium. And in that case, we have almost an infinite supply, literally actually an infinite supply of energy. If you produce more energy, that's what you consume. A third consideration of going to high temperatures is that it allows us to produce hydrogen by dissociating water. So we can convert nuclear energy into another energy storage system, which would be hydrogen. And in that case, we can use the fuel cell as a replacement for the existing internal combustion engine. So there are three advantages there: higher efficiency, an unlimited energy supply through breeding, and the third advantage is going to be the ability to use thorium. So we'll come back to this when we cover the chapter, but I would like to go and digress a little bit and look at why is it that we need to decarbonize our economy. Well, of course, for the climate change that is occurring, you could see how parts of the country are suffering and people in Canada by the dozens dying from excessive heat in the atmosphere. And in that case, you'll find that also we need hydrogen as a future energy, not energy supply per se, because the energy supplies are going to be nuclear and renewables. It could be wind and other sources of energy. I have trouble connecting to the link here, so our internet is not very stable today. Well, but we'll get to it eventually. Uh-oh, that is not what I am looking for. It went to the wrong place. Energy, origination, and decarbonization. If it gives us a hard time, we'll find a different way. Here it is. So why is it that we need energy decarbonized? Well, obviously global warming, but hydrogenation of the energy supply has great advantages, and it seems that it is a vision for our future. For instance, the vision now is for an electrical car type of a system already in California, as well as in some European countries. The internal combustion engine is being retired. The idea has been there for a long, long time, dating back to 1870. And in that case, in a book, The Mysterious Island, the science fiction author Jules Verne, French author, wrote the following. So I'll read the whole thing so that we can really understand that it is some kind of a goal of humanity there. Quote, "And what will then burn instead of coal?" "Water," replied Harding. Notice that water is a combination of hydrogen and oxygen, H2O. "Water," cried Pencroft, "water as fuel for steamers and engines, water to heat water." "Yes, but water decomposed into its primitive elements," replied Cyrus Harding, "and decomposed doubtless by electricity, which will then have become a powerful and measurable force, for all great discoveries by some inexplicable laws appear to agree and become complete at the same time. Yes, my friends, I believe that water will one day be employed as fuel, that hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. Someday, the coal rooms of steamers and the tenders of locomotives will, instead of coal, be stored with these two component gases, which will burn in the furnaces with enormous calorific power. There is, however, nothing to fear. As long as the earth is inhabited, it will supply the wants of its inhabitants. I repeat this sentence. As long as the earth is inhabited, it will supply the wants of its inhabitant. And there will be no want of either light or heat as long as the productions of the vegetable, mineral, or animal kingdoms do not fail us. I believe then that when the deposits of coal are exhausted, we shall heat and warm ourselves with water. Water will be the goal of the future. Remember that the Earth is a water planet. The surface of the Earth is 70% covered with water. And when we talk about hydrocarbons, coal, as well as petroleum and natural gas, these are all dead animals, energy stored from solar energy for 200 million years that we are using within 200 years. Long before humans controlled energy supply on Earth, nature has beaten us to the path by using water. So in that case, plants use water, combine it with carbon dioxide in the famous process of photosynthesis. And in that process where water and carbon dioxide are used, you produce sugar, C6H12O6. And oxygen is released to the atmosphere on which most of the plant and animal life live today. So in that case, you find that hydrogenation becomes part of the evolution and the vision of a future for humanity in general. Hydrogen, if we have a supply of hydrogen, can be an energy carrier or an energy storage. So it competes with batteries. It is not an energy source. It is not an energy source. You use some other form of energy. And in that case, it could be nuclear, it could be wind power, solar, hydroelectric, dissociate the water. So that needs energy. There are different methods, and the most useful methods have to operate at high temperature, dissociate the water, store the hydrogen, and you don't need, like in the vision of Jules Verne, to store the oxygen. The oxygen is available there. 15% of the air we breathe is oxygen. The rest, as you know, is nitrogen. So the first use of hydrogen in making that vision of Jules Verne real was in that car here by the Bmw company in Germany. They called it Hydrogen 7. They stored the hydrogen in the tank, and they continued using an internal combustion engine. But we'll see today that the internal combustion engine is not a good way of hydrogen, even though it is environmentally viable, because when you burn the hydrogen, you produce back again, you reverse the reaction of H2O turning into oxygen and hydrogen, and you produce back water. So water, even though it's a greenhouse gas, but it is not in any way a pollutant. We cannot call it a pollutant. The car was given as a gift to then the governor of California, Arnold Schwarzenegger, when he was a governor of California. But that is not the end product here. We'll see that hydrogen can store a large amount of energy in it compared with the storage in lithium-ion batteries that are used now in cars like the Tesla or the Bolt, or all the car manufacturers are competing to build cars that use energy stored in batteries. In fact, using lithium-ion batteries, lithium is a limited resource itself. So at some point, we'll start talking about the resources of lithium. However, if you store the energy in hydrogen, you can have first longer range cars. The batteries cars are limited in their cruising range, and you can also apply lots of energy. So that approach is more suitable for trucks. And in that case, you find the Toyota company moving in this direction in terms of using hydrogen-driven cars. So in in addition to their being environmentally viable, they are also can take a longer range. So that would be two competing systems for our future transportation system. Using the hydrogen implies, as I'll tell you here, a higher energy density and a more efficient energy use in general. So we have seen first the energy flow diagram earlier in the semester, and you'll find that primary sources of energy are so far primarily dead animals and plants: petroleum, coal, natural gas. Nuclear electric is very a small amount, 8% only. But in the end, we need to transform that primary energy into both residential forms for electricity, for commercial uses, industrial uses. And hydrogen would be primarily used for here in about 30% of our energy use. It doesn't mean that it cannot be used in the other uses of energy in general. Nuclear energy stands out among all the sources of energy. This is really the mother of all energies. Even the fossil fuels are primarily nuclear energy because, as I suggested, they come from the process of photosynthesis, and the photosynthesis depends on radiation from our star, the sun, and it comes from a nuclear reaction, the fusion of hydrogen in our star, the sun. Let's look at the specific energy of different energy supplies. Specific energy means energy per unit mass. So we take it as a million joule or a megajoule per kilogram. Obviously, the beginning of civilization, human civilization, used wood, that is 10 megajoule per kilogram. Then we switched to alcohol, ethanol, in that case, is produced from the fermentation of plant material. You can ferment sugar from sugar cane or ferment the starch of corn, and that raises the energy content to 27%. Then you go find yourself go to coal. It's a higher energy density, 32, or density would be per unit volume, but it's also per unit weight, megajoule per kilogram, 32.5. Petroleum replaced coal to a great extent, 42%. Diesel fuel for trucking and trains, 46%. Natural gas is a favorite source of electricity today, that's 55%. But if you go to natural uranium, like used in the CANDU type of reactors that we covered last time, or heavy water moderated reactors, with 0.72% uranium-235, you'll find that that energy density doesn't double or go by a factor of 10. It goes right there by 4 orders of magnitude, 10,000 times energy per kilogram or specific energy. And if you use pressurized water reactors and the boiling water reactors that we mentioned, which have an enrichment of uranium-235 of 3 to 5%, meaning that we increase the presence of uranium-235 in the fuel, then that even jumps another order of magnitude, 3.7 million megajoule per kilogram. So that's why I suggest that the future of our technological civilization is going to be dependent on nuclear energy, and that's what we are studying here, as well as the renewable sources like the wind, solar, hydroelectric, and maybe ocean thermal. If you are going to be interested in energy, we want to teach ourselves the energy units, especially large amounts of energy. And when we deal with large amount of energy, we like to use the quad. The quad stands for quadrillion. Quadrillion is 10 to the power of 15. And we also like to use the British thermal units. So BTU stands for British thermal units. So when we deal with a large amounts of energy, we use the quad 10 to the 15th BTU. However, there is another unit that's very confusing. This is called the Q. The Q is not an abbreviation for the quad. It's very misleading. It is 1,000 more 1,000 quads, which is 10 to the 18th power BT U. So remember that one quad or one quadrillion, remember that we go from million to trillion to quadrillion, and then we can go to quintillion, which would be 5 in Latin. So one quad is 1,000th of a Q. If you want to stick with the SI system of unit, not the British system of units here, the BTUs, and try to use gigajoules or joules, gigajoules would be a billion joules. So 1 trillion gigajoule, 1 trillion gigajoule would be 10 to the 12 gigajoule. Giga is a million joules, so 10 to the 12 is multiplied into 10 to the 6th power. So that's, in that case, to the 9th power. 9 and 12 is 21. And you find that you can convert that gigajoule into BTUs. And we like to use the 1 trillion gigajoule as a unit, and it transforms into about 1 Q, 0.948 Q. And we can say that the 1 Q here, the 10 to the 18th BTU, is equal to 1.05 trillion gigajoule. And we can go even higher in terms of units of energy. We, from the gigajoule, which is 1 billion joule, to the terajoule, which is 1 trillion joules, to the exajoule, 10 to the 18 joules. In the United States, basically, the utility industry consumes about 33 quads of primary energy. And we end up with 18.4 quads, whereas coal, and we end up producing from the 32.8 quads of primary energy, only 10.7 quads of electricity. So what is our overall energy efficiency? It's at 10.7 that we produce as electricity, divided into 32.8 quads, that is primary energy. So the efficiency roughly of our energy supply system is no more than 33%. So there is lots of room there to improve on the efficiency of our supply system. In that case, you find that hydrogen comes to the fore, and people get interested in energy. When people are interested in energy, hydrogen comes to the fore immediately. Now, why hydrogenation? We come back to the comparison of different fuels. And in that case, we don't look at the energy, the specific energy or energy density. We look here at the hydrogen to carbon ratio. We start with wood. That is the beginning of civilization. Wood was used as an energy source. The hydrogen to carbon ratio is only 0.1. So if you go to coal, it increases to 1. Hydrogen atom to 1 atom of carbon, half atom, half hydrogen and half carbon. If you go to oil, it doubles to 2. That's why oil is favored to coal. However, there are other forms of energy supplies, hydrocarbons in particular. It's hydrocarbons, obviously, because it's hydrogen and carbon. From light sweet crude, it goes to 1.5. Clean transport fuel 2, hydrogen to carbon ratio, cetane, hexane, propane, and then we go to methane, which is natural gas in a way. That's what comes from natural gas, at CH4. You find that obviously here you have 4 hydrogen atoms to 1 carbon atom. So the hydrogen to carbon ratio is 4. You can turn the methane gas into methanol as a liquid. And in that case, it's an alcohol, CH3OH, and you find that the hydrogen to carbon ratio remains at 4. However, you can also produce alcohol from the fermentation of sugars, sugar cane in Brazil, for instance, or from beets in the United States, or from the fermentation of the starch from corn in the United States. That's C2H5OH. The hydrogen to carbon ratio is 3. So there is a trend in energy production in terms of hydrocarbons to use really a higher proportion of hydrogen. But if you use hydrogen, pure hydrogen, you'll find that the that hydrogen to carbon ratio. Carbon is 0 in the denominator, so that's infinity. So this is the ideal in terms of increasing the hydrogen to carbon ratio. The trend seems to be going into the direction of not just having a higher proportion of hydrogen in our energy supplies, but also in terms of the well-being of humanity and the wealth. We are trending towards using higher energy per individual. All countries of the world like to raise the standard of living of their the population. So you'll find that in the 1850s to 1925, coal was the primary fuel used in the whole world. And the per capita consumption that is measured in terms of tons, T, of coal equivalent, TCE, was about 1. In the 1925 to 2000, with the advent of transportation, the use of automobiles and vehicles, that has doubled to 2.3 as a maximum of per capita consumption of ton of coal equivalent. So each one of us per year uses about 2 tons of oil or 1 ton of coal for our parents and grandparents. From 2000 to 2050 today, there is more of a trend of using natural gas. Notice that natural gas is already higher in its proportion to hydrogen, CH4, than it is coal. So in that case, the energy used in tons of coal equivalent has tripled to 6 tons of coal equivalent per person. And from 2050 up on, the vision is to switch from natural gas, well, for one reason, it will be have depleted most of it into hydrogen. And hydrogen in that case will come from the dissociation of the resource that the Earth has as a water planet from dissociating water in our oceans, lakes, and rivers. And notice that the expected energy used by individual in tons of coal equivalent will jump to double. This one, it tripled during the period, but it is expected to double one more time. Okay, now if we use hydrogen, you don't do like the Bmw Company. The Bmw Company is a German company. It stands for Bayerische Motorwerken. It comes from Bavaria, Bavern. Bayerische is from Bavaria in the area of Munich in Germany. And the Motorwerken means that they make motor vehicles. They used to build aircraft in Germany. For the war, they built a Messerschmitt fighter jet. And after the Second World War, Germany is not allowed, was not allowed to build any kind of weaponry. So the Bmw Company switched from building aircraft to building very, very well-designed cars, something that people like to call a beamer for Bmw Company. So they tried first to use hydrogen with an internal combustion engine, which is fine. However, the real better use of hydrogen is to use it as an energy storage medium for what is called a fuel cell. So what is a fuel cell? The fuel cell is a electrochemical device that reverses the process of dissociating water through electrolysis. So in that case, when you dissociate water, you add energy in the form of heat. And in that case, when you add the heat, you dissociate the water into its 2 components, the hydrogen and oxygen. However, the process can be reversed. If you recombine the hydrogen and the oxygen, oh, you get back electricity and some heat. So the process is called the fuel cell, and this is a diagram of the first fuel cell ever made, the Grove fuel cell. It consisted of 4 large cells shown in the diagram here. The name of the inventor is Mr. Grove, and he had the hydrogen in some tubes and oxygen hydrogen here. in some tube and oxygen in another tube. Obviously, he's wrong in his drawing because H2O means that by volume, hydrogen would be twice the volume of the oxygen. When you basically combine in an electrolyte, in that it could be just tap water, the hydrogen, the oxygen, he shows here that an electric current starts moving between the electrodes. So that is really what a fuel cell does. It reverses the process of electrolysis. And then he shows that as he uses that current, he can run it in another cell and dissociate the water into the oxygen and hydrogen. So he's suggesting basically a perpetual motion machine, which cannot really operate, but the idea of a fuel cell is definitely demonstrated in that process. So how does a fuel cell work? The fuel cell involves two, what's called in electrochemistry, two half reactions. In one reaction, the hydrogen that you are feeding into your cell, the two hydrogen molecules, are ionized, meaning that the electrons are stripped out of the two molecules of hydrogen here, giving us 4 electrons and 4 ions, positive ions of hydrogen. The 4 positive ions of hydrogen then combine with oxygen that we bring in, not necessarily from storage, maybe on a nuclear submarine, that would be from storage. If it is equipped with, in fact, some submarines, particularly in Sweden, are using fuel cells that provide them with complete silence in operation, major need for a submarine in that case. So the oxygen now is brought in from the air for a fuel cell engine, combined with the 4 ions of hydrogen, and basically with the 4 electrons, you get back the water. So initially we start with water, and by adding energy, heat, and electricity, we turned it into hydrogen and oxygen. In the fuel cell process, we reverse the process. We take the hydrogen, combine it with hydrogen, we get back the water. So if you add the 2 equations here, you'll find that the 4 electrons and the 4 electrons cancel each other, and the 4 hydrogen and 4 hydrogen cancel each other, and we get back 2H2 plus O2, giving us 2H2O. Notice that here the electrons become freed in the process. So as the electrons are freed, they can go out in an external circuit, and in the external circuit, that is a current. So you take the current now to a much simpler engine, an electric motor rather than an internal combustion engines. And electric cars, in fact, are much simpler in design, and they're because they don't have the same large number of components that need maintenance and care like an internal combustion engine. Basically, you'll find that that Grove fuel cell now in its modern form takes the form of small cells. Here is a diagram of how this would happen. You need an electrolyte, and on both sides of the electrolyte, you place a platinum cathode or anode. The anode would be the negative sign, and on the other side, you place another. That's the ideal kind. Platinum is very expensive, so you use other materials as cathode and anode. The cathode would be the positive electrode. And once you create that situation with an electrolyte could be water, or it could be just a sheet of that transparency acetate sheet. You'll find that if you provide on one side of that electrode hydrogen in, and on the other side you bring in air, you'll find that the electrons start flowing between the cathode and the anode into the electrolyte, and now you have a current to be established. So the current goes to an external circuit into an electric motor, and in that case you convert the energy in the hydrogen back into an electric current. And in that case, one single fuel cell like this produces about, as we'll see in a calculation pretty soon, it produces 1.2 volts. So what do you do? For one single cell, you create a stack of those cells, each one of them 1.2 volts. So if you want a 12 volt, like for a car battery, maybe that it would be 10 of those cells added to each other. So in fact, what you have here is a succession of plates. Each one has two, one cathode, one anode, an electrolyte in between them. And then you stack them in a fuel cell stack. It's a very simple type of an engine. There are many types of fuel cell types that people have been researching and exploring. Some operate at high temperatures and some operate at low temperatures. Obviously, when you reverse the electrolysis process, you get heat released. Some of the types of fuel cells are the phosphoric acid fuel cell. You may like to read more about it. It has, most of them have the same half reactions, one at the anode and one at the cathode, where the electrons really become free to move into an external circuit. Polymer electrolyte membranes, these are not using high temperature like the previous one. You could use materials like Teflon maybe. Solid oxide fuel cells is another form, and people are researching and inventing many new types of fuel cells. In the end, the configuration could look like this, is that you would have an electrolyte with a cathode and an anode on both sides of it. And on top of the cathode, you allow grooves in maybe some plastic material where you bring in the fuel. The fuel does not have to be purely hydrogen. It can be something that contains hydrogen. So, well, you can use methanol, like alcohol maybe, but in that case, you end up releasing some form of carbon. Or you can use methane and you release a little amount of carbon to the atmosphere. The oxidant could be just plain air. It doesn't have to be pure oxygen. And in that case, you find yourself with a configuration that looks like this. This is an actual fuel cell stack, 3 of them, as you could see. And these are the grooves where the hydrogen is being fed and the air is being fed. And in between them, you have the electrolytes. Obviously, reversing the electrolysis reaction produces some heat. So you really have to cool it. But you also have to cool any batteries, like in the Tesla cars, you'll find that the radiator now is replaced by some heat exchanger in the front where you have to cool even the chemical batteries. You could use a direct methanol fuel cells. That would involve a smaller release of energy. Notice that the energy carbon to hydrogen ratio here is 4 in the methanol. Methanol is an alcohol that is based on methane, methanol, methane. Ethanol is more like an alcohol produced from biological matter. You could use a molten carbonate fuel cell. You can use an alkaline fuel cell, and you can use regenerative fuel cells. So how does the generation of fuel cells function? It's an electrochemical process. People who study electrochemistry or the processes of having a combination of chemistry and electricity tell us that the energy has to be conserved. So the total fuel chemical energy should be equal to the electrical energy produced plus the heat energy that is released. The power that is delivered by a fuel cell, since it produces a current I and the voltage V in watts, is the product of I, the current, multiplied into V, the voltage. So the units here would be coulomb of the current and V, the voltage. And the IV becomes the watts. Comes apart the electrochemistry that tells us that the Gibbs free energy, delta E, or the free energy change at a given temperature is equal to the change in the Gibbs free function, the delta, the total energy released, divided into N, which is the number of moles of electrons per mole of hydrogen in the reaction, divided into a constant of electrochemistry, the Faraday constant. And the delta G, the free energy or the change, the Gibbs free energy change at the given temperature is equal to the change in enthalpy delta H minus T. And please, 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 T, when we deal with thermodynamics, is always in kelvins, 273 plus degrees Celsius. I had some people in the exam calculating the efficiency with degrees Celsius. You know, you cannot use degrees Celsius. You get a wrong number, an overestimate, obviously, when you do not use the Kelvin temperature. So this is a Kelvin, 273 plus degrees Celsius, and it relates the change in enthalpy to the change in entropy, delta S. When you combine the two equations, you can get that delta E, and the delta E is IV. So you can calculate really the voltage that you can get from a fuel cell. So let's use that equation, which says that the change in energy is T delta S from the Gibbs function minus the change in enthalpy divided into the Faraday constant multiplied into N. So let us take an example for this, and I'll ask you to recalculate it yourselves. Let's take room temperature. Some people say it's 20 degrees. Some people say it's 25 degrees. So let's take it as 25 degrees Celsius. So in kelvins is 25 plus 273. That is 298 kelvins. And let us use let us use the pressure of 1 atmosphere, atmospheric pressure. And in that case, according to the equation that we derived right here, equation 26, delta E is equal to T delta S minus delta H divided into NF, we can calculate the voltage that we get. So what is the voltage that we get? Delta E is T, the temperature, at room temperature 298 Kelvin, multiplied into delta S for atmospheric pressure. The change for a typical fuel cell is minus 163 joule per Kelvin, minus the change in entropy, again, typically minus also 285,000 joules, divided into the Faraday constant, which is joules per volt. And the N in our case for water is 2. So in that case, if you plug in the number, you get 1.229 volts. So if you are operating your fuel cell at room temperatures, that's what you get, 1.229 volts. It's very obvious that if there is heat generated, your fuel cell is not to be operating at room temperature, maybe at 100 degrees Celsius. So in that case, you find that your delta E in that case can be slightly higher. In any case, here it is, the delta S is typically minus 163, the delta H minus 285,000. So please be careful with the signs. Minus minus becomes a plus here. And that term becomes negative. So if you go to higher temperature, you'll find that the voltage you produce is going to be lower. In that case, to produce a certain amount of voltage, you have to use an extra number maybe of fuel cells. So I suggest here, if you operate a fuel cell not at room temperature, the 25 degrees Celsius, like we assumed here, if you operate at the fuel cell at a higher temperature, because heat is produced in the process, you find that the voltage becomes slightly lower. So you find that you get a voltage decrease for higher operational temperatures. And in that case, if you use air instead of pure hydrogen, if you use humidified air instead of dry gases, you find that you get even further decreases. And in that case, say that if your calculation tells you that you want to get 12 volts, say divide into that 1.818 volts, you say, oh, I need 10.5 cells. Obviously, there is nothing like 10.5 cells. I'll give you a design problem. And in that case, you need to use maybe the 11 cells. So in that case, typically, you operate at 1.16 volts at atmospheric pressure and 80 degrees Celsius. Hydrogen production, there are now many methods that people are competing in terms of research in producing hydrogen. one interesting approach is to come as close as possible to what nature has achieved, the photosynthesis process. So in that case, you try to get basically plant type of electrolysis. Microbial fuel cells would have two electrolytes separated by a barrier here, and then try to use solar energy directly, releasing carbon dioxide in that case, and create a current between a cathode and the anode with a separation between them. And hydrogen can be released, in fact, and stored. And at the same time, you can have a power source. The power source can be solar radiation in that case. So there is future research along this line. Now we have to, if we think about hydrogen, it's a great challenge to engineers and scientists because we all know that hydrogen is extremely reactive in air. And you may have watched at the Fukushima accident when it happened, those hydrogen explosions. And humanity have seen that in other situations, like the most famous situation that you can watch on YouTube. Some movie makers were basically recording the landing of the Hindenburg, which was a dirigible coming from Europe and landing at, I think it's Elmhurst in New York. As it was landing, some spark occurred and its hydrogen exploded, and people were falling off the Hindenburg. And in fact, I'm told that on the side of my parents-in-law, one of the uncles perished in that accident. So Germany had those Zeppelin dirigibles used for transatlantic flight between Europe and the United States. And they didn't use a better gas, which would be helium, because of basically the export of helium from the United States to Germany was banned. Why? Because those balloons in the First World War were used for reconnaissance of troops along on both sides of the trenches in warfare, and they were also used in directing artillery fire. So in that case, the Germans were forced to use hydrogen in the dirigible, the Zeppelins, and it ended up in a very, very tragic way. And that led to the extinction of the whole technology. We don't use the dirigible for transatlantic flight anymore in general. Fuel cells have many applications. They started really by NASA in space exploration. Remember that rockets in space need an oxidant. So if you have a rocket in space, you need both an oxidant, in that case oxygen, and you can use also liquid hydrogen. So, and the result, in fact, you get water, so you can also feed the water to the astronauts. So NASA really pioneered in the fuel cell technology in the 1950s. And they were seeking self-contained energy sources on its manned space mission. They are much simpler and more compact than solar array sources, and they are more portable than large batteries as a power source for space vehicles instrumentation. So fuel cells have been used in the space program, and then the technology spilled off now to the civilian sector. The first major use is in large cities where smog is a problem, like Los Angeles, California. So they are used in transportation and specialty vehicles like trucks or buses, in fact. In that case, you don't need to use hydrogen even as a fuel. You use a source of hydrogen, which would be ethanol or methanol. So this is a 50 kilowatt fuel cell power plant using a methanol reformer, that it's called. So in that case, it's methanol. Definitely there is carbon released when you use methanol, but you use the hydrogen in the methanol or the alcohol from natural gas, but it's much, much less than if you would have used a pure hydrocarbon like gasoline or kerosene. Some people are starting to use fuel cells in residential power generation, especially in remote locations. Defense applications are interesting because if you are in the field and you have a computer and you depend on a battery, you have maybe a maximum 6 hours, 7 hours of a battery charge. However, if you have a small bottle of alcohol, methanol, then you can have maybe a whole day, 24-hour charge that you can use. Handheld devices may find application in laptop computers where you can get uninterrupted 20 hours of uninterrupted use in general. Obviously, we are talking about the Tesla cars, and however, it shows us in that diagram that the Ford car company has been thinking about it too. They called it the P2000, but Tesla and Elon Musk beat them to the game. You could see here that you'd have a hydrogen tank in the back of a vehicle, automobile vehicle. You place the fuel cells behind it to protect them from a collision from the back. The hydrogen feeds into the fuel cell, creates a current. With a wire, you take it to the front to an electric motor that rotates the engine and drives the car. So that is a very simple design. That's why the Tesla cars are very, very popular, because they contain less parts. They need less maintenance. And however, they have their drawbacks too in terms of range or cruising range of operation and the long time that they need to be recharged. It is necessary for us to consider hydrogenation and decarbonization because coal is a really very dirty kind of fuel. It causes great unnecessary deaths. The first effects of burning coal appeared in the Meuse Valley in Belgium, 1930. They basically used coal to power their factories. It led to 60 deaths and 6,000 illnesses. In Pennsylvania, here in the United States, 20 deaths per year were normally expected, or actually in a 4-year period, during which 6,000 of the 14,000 people in the valley became sick. Imagine half the people in a population becoming very sick. There are about 50,000 deaths in the United States, 50,000. I'm repeating here, this is 50,000 deaths caused by air pollution, of which 10,000 to 20,000 are to be attributed to coal burning. So if we consider the lower range, 10,000, and multiply, divide it into the 2 million deaths that we get per year in the United States, you'll find that 0.5% or 1 out of every 200 people dying per year are dying prematurely, unnecessarily, from coal burning air pollution. So we need really to reduce air pollution even further. The methods of extracting energy from coal haven't changed over the last 200 years, even though some people are doing research on trying to isolate the carbon dioxide into deep formations, saline water formations, or into depleted natural gas fields. Coal burning for electrical generation releases 13 million tons, not just carbon dioxide, but also sulfur dioxide. And sulfur dioxide, or the SOxes, because we get SO and SO2 in the air, eventually turns into, by combination with air, into sulfuric acid. And combined with fine soot particulates, it forms sulfate particulates, as linked to 45,000 premature deaths in the United States annually in general. It's not just the United States that have a problem. In China, and that's a good reason for China to be switching big time into wind power and solar power as renewables, as well as nuclear energy, building nuclear reactors. So it is used primarily in the Guizhou province in Southeast China. It has caused a great amount of deaths from poisoning with arsenic. And the symptoms appear as freckled skin or squamous cell carcinomas, which are cancers. 10 million people are afflicted by fluorosis. It contains fluorine also, which can soften and disfigure teeth and bones. And basically, the farmers use the coal that they mine themselves from the hills to dry their food, and they use it indoors in general. Chinese coal contains 35,000 parts per million of arsenic, which is poisonous, compared with United States coal that contains only 22 parts per million of arsenic. Since the cleaning up of coal burning through pollution control technology remains in large measure an exercise in wishful thinking, some people think so, adopting hydrogenation becomes a must for our future in general. Now, if we consider nuclear energy, the generation of nuclear energy provides us with a practically unlimited source of energy for our future. And in that case, we can store that energy also in hydrogen. Hydrogen becomes a battery in that case. So in that case, you can think about fission reactors waiting for a future where we can control fusion and can use fusion reactors in that case. If we want to use fission reactors, the high temperature gas cooled reactor is an option. One of the options is what's called the pebble bed modular reactor that I'll describe in the chapter on the high temperature gas cooled reactor. So the high temperature gas cooled reactor becomes a necessity because we can use electrolysis of the water, just circulating a DC current in water, dissociates it into water and hydrogen. However, if you provide a high temperature, the process becomes much cheaper and much more economic. You could use also the molten salt advanced high temperature reactor. We'll look at this in an upcoming chapter. So using the high temperature becomes necessary for producing hydrogen. How do we do this? Well, we use what's called high temperature electrolysis. You don't carry out the electrolysis at room temperature, you carry it at high temperature. Why is that? Again, it's a matter of electrochemistry. The energy required for decomposing water into hydrogen and oxygen, delta H, in terms of enthalpy, is equal to delta F, the required electrical energy, plus T delta S. Delta S is change in entropy, and T is the Kelvin. So that's definitely heat here, and this is electricity. So the energy needed to dissociate water is partly heat, and part heat in second term, and electricity the first term. Electricity is an expensive form of energy because you start with heat and turn it into electricity with an efficiency of maybe 1/3 if you use existing light water reactors. So in that case, you find that you need a combination of heat and energy. And the diagram here tells the whole story. So it tells us that if you go to high temperature, your electrical input becomes smaller in dissociating water, and your heat input becomes larger and larger because the delta H, the total energy you need to produce, is a combination of the heat energy, the heat input, and the electrical input. So high temperature electrolysis is needed. So what do we need here? Oh, high temperature. And high temperature implies a high temperature reactor. Reactors that are designed to produce high temperatures. And it almost becomes necessary because the process of producing electricity from hydrogen in a fuel cell has a high efficiency. The process for electrolysis also has a high efficiency. But the electrical efficiency is where we have a problem. So if we take the electrolysis process with an efficiency of 0.9, 90% efficiency, and you take an electrical efficiency of 40% that is typical of the high temperature gas cooled reactor, the hydrogen efficiency is the product of the two, the electrolysis efficiency multiplied into the electrical efficiency, which comes to 36%. Existing nuclear power plant operate at 33% efficiency. However, you cannot use existing nuclear power plants, the light water reactor. If you use a light water reactor, the efficiency is only 30% and multiplied by 0.9, and it decreases below that's 36%. So some people who say that the process is not feasible because of the low efficiency, yes, maybe with existing designs of nuclear power plants. But if you go to the high temperature power plants, high temperature gas cooled reactors, then the hydrogen efficiency becomes a meaningful process in general. Or if you have an efficiency in the high temperature gas cooled reactor of 60%, then the total hydrogen efficiency can be even improved to 54%. So this is a process that in which we can produce hydrogen as high temperature electrolysis. But there is another process that also uses high temperature, and this is thermochemical processes. So you use what we are going to call the high temperature gas cooled reactor. You get little pellets of fuel that could be uranium-235, and you add to it thorium. And when you add the thorium-232, neutrons are absorbed in the thorium-232, produce uranium-233 that can fission, and then you surround that little tiny pellet, the size of a grain of salt or a grain of sugar, by different layers of pyrolytic carbon and graphite. And in that case, you get basically a very, very, very good containment of any kind of fission products release, even if you operate at high temperature. Graphite is a good moderator for neutrons. It has good thermal inertia, and it can take very high temperature. So in that case, we talk about the pebble bed modular reactor for providing the heat. There are several processes, thermochemical processes, that can use that high temperature heat. There is one called the hydrogen sulfide process. There is the iodine sulfur process, and there is a sulfuric acid thermal methanol process. All of these are thermochemical processes. So that's of great interest to our chemical and mechanical engineers. So let us look at the last three processes. You start with a chemical, obviously here, that's sulfuric acid. And when you provide heat to it, you dissociate it into water, H2O, steam in that case, and you produce sulfur dioxide, and oxygen is also released. This reaction is carried, as you could see, at a high temperature from 800 to 1,000 degrees Celsius if you want efficient hydrogen production. In the iodine sulfur process, you add to this now heated sulfuric acid iodine, and you add iodine as a vapor, that's I2. It combines with the SO2, the sulfur dioxide, and the steam, and produces hydrogen iodide, plus it returns back to the sulfuric acid. So if you add the two equations, 28 and 29, you'll find that sulfuric acid cancel, SO2 and SO2 cancel, and what do you end up with? You end up with 4 hydrogen iodides turning into hydrogen and iodine, and you take that iodine and feed it back into the process. So in that case, you get hydrogen separated from water, and notice again the temperature, 800 to 1,000 degrees Celsius. So we need high temperature. So this means that we cannot use existing light water reactors, a PWR, or the boiling water reactor, or the pressurized water reactor, or the boiling water reactor. And if you want to have high temperature electrolysis or thermochemical processes, we need to change the design of our existing reactors into the high temperature gas cooled reactor. And that justifies our next chapter, in which we are going to be trying to look at the high temperature gas cooled reactor. In addition to the need for future hydrogen production for a hydrogen-based economy, which is first non-polluting, non-carbon, as well as the possibility of breeding using the thorium cycle, we have to think about improving energy efficiency in general. So in parallel to the movement today in research and development of technology of hydrogenation, there is a need to improve the overall efficiency of energy use. We calculated it at the beginning as being only 1/3. Basically, the overall efficiency of the energy system advanced from the low value of 1% in the year 1000 to no more than 2% in the year 2000. The hydrogenation of the energy supply is expected to restart the construction of a new generation of safe nuclear fission plants and eventually encourage the development of even safer fusion systems. If we move to fusion, we can also get very high temperature operation. And this will be in addition to whatever other supplies can be provided with wind, which is really moving fast, as well as solar energy methods. I'll stop here. This is really the justification why we need high temperature reactors. So if you have questions, you can ask them in the chat room, or I'll basically listen to you by making you a co-host. I don't see any questions. Please read the material. However, now we go and having made the justification for the using high temperatures, let's go and look at our famous high temperature gas cooled reactor. So we made the justification for it. In that case, when we deal with the high temperature gas cooled reactor, we'll look at some pilot plants that were in fact built already. And those plants that were built used also the thorium fuel cycle. They experimented not just with the use of the uranium fuel cycle, but using the thorium fuel cycle. So you find that in those plants, thorium became prominent. So it combines really three very interesting goals for energy, future energy systems. First, you need the high temperature, meaning higher efficiency. You get the breeding in thorium, and you need the high temperature also for hydrogen production. So basically, it is an interesting three-pronged approach to a future energy system. Let us compare again, because I'm saying that our existing light water system is not really conducive to a hydrogen economy. So we have today the light water reactors that we covered so far, the pressurized water reactor and the boiling water reactor. They all use the steam turbine Joule cycle. If we switch to the high temperature gas cooled reactor, even though some designs still go and use a steam cycle, doesn't make sense. You go and use the gas turbine or the Brayton cycle. That's with a compressor on the same shaft as the turbine. That's what leads to higher efficiencies. Look at here the efficiencies, theoretical efficiencies that we can reach with a gas turbine cycle, 70%. So we provide only 30% to maintaining the flow or the asymmetry in the production process. The steam turbine cycle that exists today is no more than, at most, 35% efficient. We have doubled, we doubled the efficiency of the cycle by going to the Brayton cycle compared to the steam cycle. However, that comes in association with using high temperatures. The steam in the light water reactor system is 300 degrees Celsius or 350 degrees Celsius. And here, if you use helium as a coolant, well, we can reach 1,000 degrees. So that makes thermochemical processes and high temperature electrolysis feasible in general. Nevertheless, even if the goal is not the production of hydrogen, you can think about going to high temperature in three different ways. You can produce process heat. So on campus here, we are producing heat by a combination of natural gas and coal, and the campus buying wind electricity from a wind farm southeast of the campus. But a high temperature gas cooled reactor would produce either process heat, it can be used for power generation, and can be used for hydrogen production. So it has a large range of operation. If you want just process heat, you produce temperature in the range of 250 degrees Celsius. If you want to produce electricity, you start operating at 600 degrees Celsius. However, if you want to produce hydrogen, you need to go to the 950 degrees Celsius. Existing light water reactors would only operate within that range of power generation. They can only produce electricity. They cannot produce the hydrogen. Or they can produce it, but at a meaningless, very low efficiency. As I suggested, in addition to getting high temperatures and higher efficiencies and being able to produce hydrogen at high temperature from high temperature electrolysis and thermochemical processes, you'll find that high temperature gas-cooled reactors provide us with the ability of now making nuclear energy an unlimited energy supply by breeding of uranium-233 from the more abundant in the Earth's crust thorium-232. And in fact, these are different plants that were built on a pilot basis. In the United States, a plant was built at Peach Bottom, operated over the period of 1967 to 1974. I'll show you pictures of it. The Dragon was a system built in the UK around 1975. Germany had two pilot plants built, the AVR and the THDR, and THDR stands for thorium high temperature reactor. See, thorium here is prominently shown. And the design also includes not two approaches, one that we are going to call the pebble bed design, pebble bed spheres here, that was pioneered in Germany. And in the United States, we had a plant that operated for a while that used hexagonal blocks of graphite. Their power was very limited. They were not at the 1,000 megawatt level in terms of producing electricity. 4 cent brain and the THDR produce only 300 megawatt electric per power. Notice the efficiencies here, 300 divided into 750 gives you an idea about the delta T, or the range of temperature. However, notice the temperatures too. The helium outlet temperature was not the 350 degrees that we meet in existing light water reactors. This is in the range of 950. So we are reaching the 1,000 degrees Celsius. Add to it 273, it gives you Kelvins 1273. The pressure of the helium though was high, 48 atmosphere. And this is the most important aspect of this design. Thorium and uranium carbide were used in the 5 designs of the pilot plants. They used a gas coolant. They differed in the design of the pressure vessel. The 2 latest designs, the 4 cent brain and the THDR, used a pre-stressed concrete pressure vessel, whereas the 3 earlier ones used a steel pressure vessel for the reactor in that case. So let us look at some actual pictures so that you can see really that these things existed. And that was basically checking the future of nuclear energy in terms of, while the idea there was breeding and higher efficiency. This is a 40 megawatt electric high temperature gas cooled reactor. It was designated as Peach Bottom that I have shown in the table. This is the British Dragon reactor at Winfrith Heath in the UK. And here is the Fort St. Vrain in Colorado, plant built by General Atomics. That plant had a problem with the steam generators, so they stopped operating the nuclear part of the plant and they turned it into coal. But it was not a problem with the coal part of the nuclear part of the plant, it was a problem with the steam generation part. And it shows us here the blocks of graphite that were used at Fort St. Vrain. You could see it's a hexagonal kind of a graphite block. It was, these were being lowered inside the core, and those graphite blocks have tubes in them. If you look very carefully, you can see tubes that would circulate the helium gas and tubes that had the fuel inserted into them. So that is one of the approaches to high temperature gas cooled reactors using graphite. The second approach is to use a pebble, almost like the size of a tennis ball. So this is a scanning electron micrograph of one little tiny grain of uranium And you could see it is covered by layers of graphite, one layer upon the other, and then with also silicon carbide. Silicon carbide can take very high temperatures. In fact, the lining of the space shuttle for re-entry or re-entry vehicles in general uses that silicon carbide. So each one of those tiny little things the size of a grain of salt or a grain of sugar now are embedded inside a larger graphite container. You could see those tiny little pieces there. Again, as another layer against the release of radioactivity. So it's a very, very safe reactor in terms of containing radioactivity in the case of an accident, because graphite has a very high thermal inertia. And because it has a very high thermal inertia, it can take very high temperatures. I've shown that diagram before. Those fuel spheres are called the triso. Triso because they have both uranium in them as well as the thorium. And in that case, what you do is that you place those pebbles in a container. As I said, they're the size of a tennis ball, graphite balls, and you can operate them at a very high capacity factor, because all you do is feed those pebbles from the top of the reactor to the bottom, extract them from the bottom as the fuel in them is being used. So high capacity factors would be expected from those types of reactors. Are also very safe, not just from the temperature effect, but because they avoid having too much piping, so that it's an integral type of a design, like the IRIS design that I have shown from the General Electric company. And this is based on submarine technology, where the Navy the United States Navy has 9 generations of reactors, whereas we have only 4 generations of land-based systems. So you could see here that you have the reactor core here, where you feed the pebbles from the top and extract them from the bottom. And you circulate the coolant into the pebble bed. It's the pebbles in that case. And then it goes to a steam generator. And the steam generator doesn't use piping on an outside steam generator. You find that the steam generator is contained in a single pressure vessel. Unfortunately, they use steam generation, when in fact, if you use a gas, you should be using the Brayton cycle. So they need to redesign that system to use a Brayton or the steam cycle. Another interesting experiment that was undergone with the THTR is the heat rejection to the environment. In existing power plants, we can use those cooling towers, like I've shown you the content and the design and the interior of a boiling water reactor cooling tower. And that uses some basically makeup water from a lake or a river, or a lake or a river. However, the Germans on the TFTR experimented with a metallic cooling tower. So the heat transfer now is from the metal to the air. And why do you experiment with this? Because if you use, if you have a supply of water, obviously you can sacrifice some part of it to produce the steam that is generated in cooling the water after it is used in the condenser. But with a metallic tower like this, you don't need any water. So what does it mean? It means that it can be used in arid environments where you don't have a supply of water, and that also would be centers away from population centers, so that it would provide another level of safety in operating nuclear reactors. So for arid regions of the world, the TFTR pioneered the idea of using metallic or non-water, non-H2O water tower. You notice here that they are writing here the betreten, verboten, meaning forbidden. They don't have people access to it. So in that case, if you use the designs that have been suggested for high temperature gas cooled reactors are the pebble bed modular reactor. PBMR is the acronym for it. And this is designed by South Africa, by the Sasol company. And you could see here now that that is the correct design of a gas-cooled reactor. Notice that you have now the turbine on the same shaft as a compressor to a gearbox to the electrical generator. So that is using the Brayton cycle, the gas turbine cycle, not the steam cycle like the THTR. If you use high temperature, you might as well use the Brayton cycle that can provide you with a very high efficiency. You don't have a condenser in that case, you have a pre-cooler where the gas from the compressor circulates back into the turbine. You need basically some heat rejection through a recuperator there, and the reactor is enclosed in a pressure vessel. That reactor, unfortunately, was never built, even though the Clinton power plants thought that for a while about, because the site was built to accommodate 2 units, but they built only 1 unit. They thought about adding a new unit that would be an experimental reactor of that kind. So this is some kind of a very, very far-fetched design in the future. This would be the flow diagram for it. And the main desired feature is that it will have a high efficiency, and either that they can use a pre-stressed concrete pressure vessel to contain the reactions, or they can use a steel vessel. In that case, the reactor would be placed underground. The pebble bed modular reactor has a tremendous amount of safety feature, and but we should really think about using the Brayton cycle, not the steam cycle with cooling with a gas. That is the right thing to do. So this is a conceptual design, as you could see here, now with a gas-cooled reactor inside a steel vessel, and then you have a second part of there, which would be the compressor and the electrical generator plant. You'd have an intercooler, a recuperator for the gas turbine cycle. So it's new technology that needs to be developed for a future where we try to decarbonize and hydrogenize our energy supplies. There are 2 pilot plants existing now in the world. And as I suggested, they depend on 2 concepts. The concept that was used in the Ford-St. Vrain reactor, which uses a prismatic hexagonal graphite block. It's shown in a photograph earlier, where you have tubes. Some tubes have fuel in them, stacks of carbon dioxide. Actually, they use more like, in the middle, it's metallic fuel, in fact, and then covered with silicon carbide, SiC, and pyrolytic carbon to contain any fission products from the chain reaction. Those little pellets that are 2.5 centimeters in diameter are placed in tubes, and then you have other tubes where the coolant circulates. The heat is generated in the fuel, of course, then it propagates to the graphite, and then the coolant moving through the graphite holes extract the energy. And that idea is being used in a reactor, the high temperature engineering test reactor. It is placed underground. And I think this is a plant that is existing today as an experimental plant. It's a 30 megawatt thermal using the prismatic fuel, and it's operated by the Japan Atomic Energy Research Institute. And they are trying to reach temperatures of a maximum of 950 degrees Celsius for, again, as I suggested, the goal is the development of a hydrogen production system using high temperature gas from the high temperature gas cooled reactor. So this is a very important effort conducted by Japan. Not only Japan, but also China has a pilot plant along this line designated as HTR-10. And this is, it started operating in the year 2000. And in that case, they use the pebble bed concept. please understand the difference between the two concepts. A pebble bed is those balls, tennis ball size pebbles, 6 centimeter in diameter. And the core outlet temperature is 950 degrees Celsius. So again, the idea is to produce high temperature process heat to produce electricity. And that is at Tsinghua University in China. So both Japan and China are contributing to the effort in developing those types of systems. So in conclusion, the high temperature capability and smaller unit size offer the prospect of non-electrical applications. For instance, you can use process heat, and process heat can be used, say, in refineries, or the real need for heat is for the desalination of seawater. The world is facing a shortage in freshwater supplies, especially in arid regions of the world on the shores of deserts like the Sahara Desert, North Africa, or the Arabic Peninsula. And the HDGR has a very high level of safety. It can produce high temperatures at 1000 degrees almost from the reactor. It can be used in very different fields. But if we use thorium too, wow, we are really developing an infinite energy supply. We can breed more fuel than what we are consuming. I'll give you a small problem here. Use the table that in the text to estimate the efficiencies for the different concepts for process heat, power generation, and hydrogen production. I'll stop sharing here and go to the chat room if there are more questions about that chapter. If there aren't any, I'll go and cover another chapter. Okay, I'll go back to sharing. And what comes next is now what are the research and development concepts that are being pursued today? And that comes in through the 6th chapter here about the concept of the 4th generation reactor concepts. We are building and operating today what we call the 3rd generation reactors. However, the 4th generation is on the drawing boards. And remember that nuclear power plants across the globe are producing 16% of our electricity today. And if we are going to switch to a hydrogen economy, decarbonize our electricity production, there is no way other than going to nuclear energy and a mixture of renewables and nuclear energy. As a 3rd generation reactor, I've shown already in the chapter on the pressurized water reactor, the advanced passive 1000, AP 1000 reactor that is being built in different parts of the world now with the chimney kind of a concept as an extra safety feature compared with existing light water reactors. However, on the drawing boards, we have the now the 4th generation. The 1st generation operated from 1950 to 1970. The 2nd generation up to 1990, that included the boiling water reactor, then the light water reactors in general using light water. In Canada, it included the CANDU reactors, and in Russia and older Soviet Union, the VVER 1000 and the RBMK 1000 of what happened where the Chernobyl accident occurred. 3rd generation is now being built today and operated. This is the advanced light water reactors, including advanced boiling water reactor and what is called System 80 Plus. By 2010 to 2030, existing today, this includes the AP 1000 that I have shown and the AP 600. 1000 stands for 1000 megawatt electric, and 600 is a smaller size, 600 megawatt electric. And typical of them is avoiding the fact that in existing reactors, the containment concrete structure acts as an insulator. It prevents the dissipation of heat from the design basis accident where, say, a pipe breaks down during an earthquake. So the steel shell, which is the real containment of a reactor now, is not insulated by the concrete structure. There are openings at the top here that allow air to come in and then rise, cooling that steel shell. And the cooling is helped by having a tank of water on the top that sprays the steel shell, and typical of that chimney design. So this is an advanced concept that is being built and operated in many parts of the world. Coming up on the drawing board is the fourth generation. The fourth generation is what those of you who would adopt as their careers building those designing and building those reactors. The goal is to be economically competitive with other forms of energy. Coal, definitely nuclear energy is competitive with coal because we want to decarbonize our energy supply. We need enhanced safety. High temperature gas cooled reactors provide us with enhanced safety over the existing light water reactors. We need to minimize radioactive waste generation, and we don't want countries to use any produced plutonium to start lobbing weapons at each other, so proliferation resistance. So these are the four goals of what people call the fourth generation. That started an initiative between 9 countries. These include the United States, the UK, France, Japan, Canada, Argentina, South Korea, the Republic of South Africa, Switzerland, and Brazil. These are 10 countries. And they ended up selecting 6 concepts for further and deeper investigation. And again, the idea is to provide higher sustainability. In that case, they use 4 different fuel cycles. One is called the once-through fuel cycle, where you burn the fuel and then you take it and dispose of it in the same way that we mine uranium out of the ground. We take it and bury it back into the ground. Another cycle used in Japan, Russia, and France, the European countries, is to recycle part of the plutonium fuel. Remember, plutonium is being produced in existing light water reactors, not to a grade where it could be used in weapons, but nevertheless, in that case, you can recycle the plutonium instead of disposing of it, and just burn it and produce energy out of it. A full plutonium cycle would totally recycle the fuel. In the case number 2, we use a mixed oxide, an oxide that contains partly uranium dioxide as well as plutonium dioxide. And the 4th cycle would recycle all the transuranic elements that are produced so as to produce the waste that's produced from the burning of nuclear fuel. So these are the goals, 4 goals of the new initiative, or the new that people have on the drawing board. You'll find that if you use the 4th option, you transmute the produced heavy elements, the actinides, and in that case, you reach the level of toxicity of the natural uranium that you mined in the first place from the ground within 500 years. With the existing systems without transmutation, it will have to be 200 or 500,000 years before you reach the same level as uranium that you extracted from the ground. So we'll not be doing any harm to the environment. Uranium is coming from the ground with a half-life of 0.9 billion years. It is radioactive anyway. The fission products, if you use the transmutations, will become at the same level as what we mined originally from the ground within, this is a logarithmic scale, so that's 100, 200, 500 years in general. So these are valid goals. The economics are improved, the safety and reliability are higher, and the proliferation resistance also is improved to provide a safer world in general. Okay, I am going to order them in an order that seems to be the most important one. Today we talked about the need to dissociate water into hydrogen and oxygen. So in that case, we said we need a very high temperature. So the first concept is, in fact, being pursued, the very high temperature reactor, very high temperature reactor. And this is, they have, in fact, $1.1 billion dedicated to that project. and they wanted to have a demonstration, which did not happen by the year 2015. And that's a diagram of that very high temperature gas cooled reactor. So they use a graphite reactor core to produce a high temperature. And you can guess immediately that whoever is designed it is not cognizant of the possibility of using the Brayton cycle or the gas turbine cycle. They're using a high temperature reactor to produce steam, and then they take the steam to a hydrogen production plant. That is not the right way to do it. If you are going to use a high temperature, you might as well use a gas turbine cycle. So some of you may join the industry and correct the misconception here. Notice again that the very high temperature gas cooled reactor would be producing hydrogen. And in that case, when you dissociate water, you are releasing the oxygen to the environment. But this is still a goal, very high temperature reactor. Some governors of different states like Utah have been competing to get, and the technology will depend on two pilot plants, as I said, the HTR-10 in China and the HT-10 in Japan, and the previous experience in the United States at Fort St. Vrain in Jena. The second concept in the generation for reactors is a gas-cooled fast reactor. Now this is cooled with a gas, so in that case, again, you can use move from the steam cycle to the Brayton or the gas turbine cycle, and it can provide it still with a high temperature, but fast reactor means that it doesn't have a moderator or an efficient moderator. In that case, you can have the benefit of breeding. Remember that if you use a graphite core here, like the 6 plants that were built as pilot plants, you still can use, using graphite as a reflector, you can use a mixture of uranium and thorium and start achieving the dream of nuclear energy, which is breeding. And breeding provides us with an unlimited energy supply. So I put the gas-cooled reactors as a second preferential one, and immediately here you see that the designers now are doing something right. They're not using a gas and then sending it to a steam cycle. That's simply oversimplification. I don't think they are not knowledgeable about it. It's just oversimplification. But here, if you go use a gas-cooled reactor, fast reactor, so you get the benefit of breeding, but they're using really the correct design. They take the gas that comes out of the reactor core to a turbine, and then on the same shaft of the turbine, you have the compressor. So you are back to now really the ideal cycle for a gas, which is a gas turbine cycle by name, gas turbine cycle. So this is the second concept that can produce for you higher temperatures for hydrogen production. They came back with an old concept, the gas-cooled, the sodium-cooled fast reactor. They designated as SFR. It can also produce high temperatures to you, but not as much as a very high temperature reactor. The sodium-cooled reactor uses a pool of sodium in which you have a reactor core, and then you have a second loop of sodium extracting the heat from the pool of sodium, taking it to sodium to water heat exchanger, steam generator. So in that case, you could see a turbine here, no compressor, a turbine associated with a condenser. So they're using the steam cycle. So in that case, if they do not choose the high temperature for high temperature water electrolysis to produce hydrogen, it will not be reaching the efficiencies that are contemplated for the high temperature water electrolysis or thermal processes. Another design comes to us here that they're calling it the lead-cooled fast reactor. Fast because when you don't use a good moderator like water or heavy water or graphite, the neutron energy remains fast. A neutron in the range of, when it's born in fission, has an energy of 2 million electron volt, and the moderator decreases it to 0.025 electron volt. In that case, it allows you again breathing. So the ideas here are breathing. And it takes up, adopts technology that was tried by the Russians in their nuclear submarines. In that case, they used lead, or a combination or an alloy basically of bismuth here and lead. And they operated it in such a way they can produce high temperature, in fact, to have it like a safe type of a design that doesn't need pumps to circulate the coolant. So they build up a very tall chimney in the reactor. The reactor core here produces the heat. As the lead is heated, its density decreases. So it has a buoyancy, it rises, it gets to heat exchangers at the top, and then comes down all by itself by natural circulation. No pumps are needed in that case. And they take the heat to, well, it's hot enough to take it to a turbine with a compressor. So in that case, the gas turbine cycle is being envisioned in that case. But again, they are aiming at the goal of breathing. Some people suggest that if we continue operating on the existing designs of light water reactors, we are using up the cheap, because it's cheap, supplies of uranium-235. And if we continue using the cheap supplies of uranium-235 without breathing, we may end up with cheap supplies. We'll always have uranium-235. Even uranium in seawater can be extracted from seawater, but the costs will start going up. So in that case, breathing becomes the vision of future nuclear reactor systems. The Germans and South Africa did some research on using what's called a supercritical water-cooled reactor. In that case, the water is heated to a very high temperature above the critical point in the TS, or the temperature against entropy diagram. So in that case, it's a gas-cooled reactor, in fact. So you circulate the coolant in the reactor, take it to a turbine and expand it. So they're using the steam cycle, and in fact, because they're operating at 700 degrees Fahrenheit, they might be able to use the gas turbine cycle, but the water would be extremely corrosive in that case. And the last design is what's called the molten salt reactor. The molten salt reactor was experimented with in a plant built at the Oak Ridge National Laboratory. And it was a pioneering plant. It used a graphite core, and basically it used thermal breeding in the thorium to uranium-233 fuel cycle. I'll ask you today to balance the equation for breeding in thorium. When you add to thorium a neutron, it turns into thorium-233. And when you add the thorium-233 is radioactive, it emits a negative electron and turns into protoactinium-233. Then it emits another electron and it turns into uranium-233. Now it's an odd number isotope, so it's fissile. So in that case, you turn something that is not fissionable with low energy neutrons into something that is fissionable. And thorium is 4 times more abundant in the Earth's crust than uranium. So in that case, the emphasis is breeding. And you can produce high temperatures too. So you could see here a gas turbine cycle. In that case, you have the turbine on the same shaft as a compressor. And that includes, in that case, operation first at high temperature, higher efficiency. It's not a gas-cooled system. It's a molten salt reactor. The salt is a salt containing fluorine, uranium, and thorium all at the same time. It's a very safe operation because if for any, in the pilot plant, they could shut down the reactor by emptying the salt from the bottom into some emergency dump tanks and go back home for the weekend. Because the fuel is in liquid form, they use the chemical processing plant to continuously eliminate the fission products. Hence, they didn't have any problem with the decay heat that caused the 3 major accidents that melted the fuel from the decay energy of the fission products in the fuel. So if you continuously use a fuel that's a liquid instead of a solid, you have basically a purified salt that goes through the reactor core, and this would be a fascinating system to develop. Every system that we have shown here has its own advocates and people who criticize it and people who advocate it, and they are really in need for a dedicated effort in research and development. Some of you may be involved in that effort. The common areas of research and development and engineering involve the different fuel cycles. Is it the molten salt that we want? Is it the graphite moderator? Material choices, energy products, risk and safety, economics, and of course, and physical protection and proliferation concerns. All of these are areas of future development. Oh, we covered today 3 chapters. I'll stop again and see if there are any questions in the chat room in the remaining time. Since we are into a crash course, if you have questions, please come up with questions. If not, we'll go and cover a 4th chapter today. Wow, that would be a record. Okay, let's keep going. Let me see here. Okay, so here we are looking at fission systems. We covered today the high temperature gas cooled reactor. We covered the 4th generation reactor, and we covered the energy hydrogenation and decarbonization. We cannot proceed further without looking at fast breeder reactors. We mentioned that if you do not use a moderator in your reactor, you can use a coolant that would be a molten metal. So these are not molten salts like the one that I've shown you, which is a salt of fluorine, uranium, and thorium, but you can use a molten metal. The first reactor that was built used a eutectic. Eutectic is an alloy that has the lowest melting temperature between 2 metals, for instance, potassium and sodium. So the first ever fast breeder reactor was EBR1, experimental breeder reactor number 1. It was followed by the experimental breeder reactor number 2, which used sodium as a coolant. So when you heat up sodium, you'll find that you can have a molten type of a system that also can get very high temperatures for you for possible hydrogen production. However, it is a breeder, meaning that those fast neutrons are able to produce more neutrons available to us in excess from the neutron that is used in the fissioning process, and a neutron that's absorbed, that leaks from the system or is absorbed in the structure of the reactor. So in that case, we can produce the dream of nuclear energy or the vision of nuclear energy in producing more fuel than what we are using today. This is an actual picture of the experimental breeder reactor number 1. It was the size of a football, really. It was very small size, and it was experimental. They kept running experiments on it to the point of damaging it to gain experience about how to operate those fast reactors. This reactor was built in the Idaho desert, and it has been turned into a museum. So if you travel towards the west during the summer, try to stop there and maybe visit it. Don't travel in that area during the winter. It's very dangerous because you can get stranded on the icy roads. It used the sodium-potassium eutectic alloy that was liquid at room temperature. That was followed by the EBR2 experimental breeder reactor number 2. Actually, the experimental breeder reactor number 1 was the first reactor to produce electricity. And they were demonstrating this by getting the electricity from their electrical generator here and lighting a string of light bulb. And that happened on December 20th, 1951. So if you are 2021, that was 70 years ago that energy was produced from. Actually, the fascinating thing is that The first nuclear energy produced was from a fast reactor. So they had on their mind the idea of breeding. That idea was superseded by the need to provide power for naval propulsion for fleets of submarines and aircraft carriers, and in favor of the light water technology. That was followed by the EBR2, experimental breeder reactor number 2. It was cooled by a sodium system. It operated successfully for 25 years and provided electricity to this city of Idaho Falls in Idaho. You could see here it uses steam cycle with steam coming up in a desert area from steam, basically steam towers. I had the pleasure, in fact, to walk on the top of the reactor while it was in operation on a stay at the Idaho National Engineering Lab over a summer stay. It was extremely well designed. It was some kind of retired because it just reached its age limit. Any technological object like a wind turbine can be operated efficiently for maybe 20 years. Same for any nuclear reactor. You cannot continue operating any capital equipment, like even a taxi cab has to be replaced after operation for a certain number of years. Sodium at room temperature is solid, so you have to keep it hot at room temperature by using steam. It was a very, very successful system. However, when the United States started thinking about building a large, not pilot plant, this was a pilot plant, obviously, but a plant at Clinch River in Tennessee, they did not adopt the pool concept that was experimented with in that design, and they switched to a loop design, coming back to the light water design. That was a mistake by the designer at that stage, which was the Westinghouse company. You could see here, it's a pool of sodium with a core immersed in it. Then the sodium is taken to a secondary sodium loop, and the secondary sodium loop would go to a steam cycle operation. The idea was adopted by the French, and they understood the basic kind of concept. And they started building their first fast reactor. Notice that France is short on fossil fuel supply. They don't have enough coal or oil. So 70% of their electricity, they are proud of it, in fact, and they should be proud of it, is produced by nuclear energy. So when they built their first fast reactor, they call it the Super Phoenix. Actually, they called the first one Phoenix, and then the second one, they built two of them, they called the Super Phoenix. And Phoenix here is an interesting way that the French are very poetic. They adopted the name of the phoenix, which is a mythological bird that is reborn back again from its own ashes, which describes the vision of nuclear energy, which I keep repeating today, which is the vision of breeding, producing more fuel than what you are burning. This is a design of that system. You could see that they use the pool design, whereas the Clinch River design that was adopted in the United States used more like light water technology. And very soon people criticized it, the technology people, and they suggested that it is outdated technology, and the whole project was abandoned. So in that case, we define what's called the fuel burnup, which is the uranium and plutonium that you breed and the fission to the total uranium and plutonium in the nuclei. That is what we define as the coolant burner. Again, you could see the core here immersed in a pool of sodium. That sodium is covered with a layer of neon. And unlike light water reactors, any depressurization of light water would flash the water into steam. So in that case, you can lose your coolant. Sodium is safer from that perspective, is that it won't flash into steam if the system is depressurized. So it operates at simply atmospheric pressure. It's not pressurized to 2000 PSI like the PWR or 1000 PSI like the boiling water reactor. However, sodium can be reactive with air, and provisions have to be provided for isolating the sodium from the air around it. This shows us again a dismantled turbine for the Supercritical, and you could see that's really very high tech use in that case. The Russians also developed fast reactors. This is their BN800. It was under the design at Beloyarsk. The Japanese have fast reactors. The British built fast reactors, and they were experimental at Chernobyl also with a mixed oxide of reactors. The Russians are developing the BN1200, which means to replace the existing BN600 reactor. And basically, all countries in the world that are really in a stage of development, like industrial countries, I should say, are thinking about a future where we can use those fast reactors. And we'll stop at this today, and I'll be available in the chat room. From Vincent Chen to everyone, why does some reactors allow breeding and some cannot? It depends on two factors. Is that Vincent Chen? I will try to unmute you so that we can also discuss the topic. The other people can be excused if you don't want to listen to the discussion, but I will make you a co-host so that we can talk. Vincent Chen, all right, here. Make you a co-host, you can talk if you have a microphone available. It depends on two factors, the type of fuel that we use and the energy of the neutrons. In general, if you have high energy neutrons, you'll find that when they cause fission, then we just can talk in the chat room. At high temperature, at high energy, the neutrons can produce more excessive neutrons in fission than they do in the range that we use nuclear at the 0.025 electron volt small energy range. So in that case, you have more neutrons available to you to absorb in a nucleus like uranium-238 that usually does not fission as readily as uranium-235. And as you absorb the neutron, the uranium-238 becomes uranium-239. It emits a negative electron. It becomes protoactinium-239, and it becomes plutonium-239. And when you have an odd numbered isotope, it can fission with any energy neutron. So that happens primarily when the energy of the neutrons is high. So it's used with what we call the fast reactor today, liquid metal fast breeder reactor. Notice that we do not moderate the neutrons. That is not moderation, say, from water or graphite. On the other hand, another fuel, the thorium now, is better in breeding when you are in the thermal range, when the neutron energy is low. So if you want to breed uranium-233 from thorium-232, thorium-232 is an even numbered isotope. It cannot fission with very low energy neutrons. But if you produce uranium-233 from it or breed, the terminology comes from biology here, as you notice, fission also and fusion, all terms coming from biology. You find that in that case, you can produce more atoms of that uranium-233 than the atoms of uranium-235 that you used earlier. And at some point, you replace your uranium-233 with only that uranium-235, and basically you have started a cycle where you have an unlimited energy supply. So it depends on the energy of the neutrons. Then you have the thermal reactors, which operate on thermal neutrons. These have moderators like water and graphite. And notice that the thorium reactors all use graphite as a moderator. Or the fast reactor, which have bad moderators. Sodium is a bad moderator. Lead is a bad moderator. It doesn't moderate the neutrons, so they remain fast and are able to produce extra neutrons that we can use to produce more fissile fuel. Fissile, in that case, is a terminology that says that the nucleus can fission with zero energy neutrons. Just adding a neutron to the nucleus can cause it to split. Just the mass of the neutron would split it. However, when you have even-numbered nuclei, like uranium-238 and thorium-232, they do not fission as readily as the odd-numbered isotope, uranium-233, plutonium-239, 9 is odd, neptunium-237. Okay, Vincent Chen, I'll make sure that I keep answering your question as we proceed further in the course. Did I answer your question? Are you in the chat room? Oh yeah, you're still there. So high energy allow breeding for even number, and low energy can allow, no, actually low energy can also allow it with odd numbers. Now, if you have time, I can go to another chapter and try to explain that in more detail. Do you have time? I do. Wonderful. Let's stay together and I'll satisfy your curiosity. I really appreciate your intellectual curiosity here. So I'm going to share the screen again. And I'll go to another chapter where this is covered in more detail. And the chapter has a title of Sustainable Energy Production. So I have to find the chapter first. Help me find it maybe by reading the chapter here. It starts with sustainable, and I'll show you a graph that explains it. This is chapter 7. I haven't covered it. Basically introduces nuclear energy as a sustainable long-term energy type of system, and discusses the idea of peak petroleum and peak fossil fuels. But I'll try to go to that diagram that will try to describe to you that idea of the extra neutrons. I don't remember exactly what it is, so I'll have to keep looking at all the diagrams I have in that chapter. We may or may not cover that chapter, but maybe I'll do it just to satisfy your curiosity here. It started as a small chapter and then grew up exponentially. I cannot find it. Maybe if I search Control F, breeding. Okay, yeah, here we have it. I hope you are still with me. This is I discuss in that chapter the process of breeding in much more detail than what we have done so far. So the requirement for the generation of more fissile material is described by what we call breeding, meaning that a factor in the generation of neutron called the regeneration factor is larger than 2. And larger than 2 because you need 1 neutron to maintain the fission reaction. And if you have it larger than 2, you allow a neutron to be absorbed or to leak from the system. And the extra number of neutrons can be used for breeding. And if we go to that figure 90 here now, it will describe that in more detail. This is, as I suggested, the process of thorium-232 absorbing a neutron, becoming thorium-233, turning into protactinium-233 to uranium-233 that can fission. And the other breeding cycle is the one happening in uranium-238. It absorbs a neutron. It becomes uranium-239, becomes neptunium-239, plutonium-239. Oh, that can fission. So you could see here an even numbered isotope. When it becomes an odd numbered isotope, it can fission. So the trick here is to turn an even numbered isotope into into an odd number isotope. Let me find that figure 90 here if I can, and that will convince you what we are talking about. Oh boy, where is figure 90? Now let me see here. Oh boy. Okay, so that's a simple explanation, but there is a graph that should show us that detail, and I will have to find it. And oh, here it is. It's 89, not 90. Okay, now that is that regeneration factor. That is the number of neutrons that are produced as a neutron is absorbed and fissioning an isotope. Now look here, if the neutron energy is high, you'll find that that regeneration factor, the number available to us, are higher when you use plutonium-239. You see here, and basically you produce 3.5 neutrons if you are at a high energy of the neutron. I'll make it smaller here. However, when you are at a low energy neutron, you'll find that that regeneration factor is highest here. This is the highest one is with the uranium-233 fuel cycle. And so it depends, as I suggested, on the type of fuel that you are using, whether it is uranium-235, uranium-233, or plutonium-239. When you have uranium-233, the best choice that you have above 2 is the thorium and uranium-233 cycle. When you are using the plutonium cycle, the best cycle that you can, in fact, you can use it for the 3 of them, but the best option you have is plutonium-239. So remember, this one is figure 89 in the chapter on sustainable energy and resource management. So you can go and look at it in more detail. I hope I provided you with some explanation here, but its time hasn't come yet in our class, but at least you know now why is it that we have different choices for nuclear reactors. All right, have a nice afternoon, everybody. I'm still available for any questions beyond the time of the class.